Live streaming is on.
Very good. Okay, so welcome everyone. It's time to wrap up everything. It's been an awesome week. And without further ado, we'll start with one of our favorite guests from last year, Artash from Toronto. The floor is all yours. I remind you have 5 minutes, so try to be focused. And the floor is yours. Please share the screen and show us what you have.
Absolutely, thank you. This past week has been really fun. Thanks to all the organizers of this event. It's been a really informative week. And I'm going to give you a quick overview about my work. So in the past year, I've been working a lot on seismic data ever since I joined the Transform community last year. And I've been working, and I learned a lot about the methodology behind analyzing seismic data and what are the cool things I could do with it. And this year, I worked on a project on measuring the effect of COVID-19 lockdowns on the decrease in seismic activity in cities. And the main methodology I used to process my seismic data was based on frequency analysis. So I could use power spectral densities to break my raw waveform seismic data into the frequencies, and then pick out what frequencies were of interest to me. Like in my project to monitor the human activity in cities, I was able to pick out the frequency band between 4 to 20 hertz, which is most affected by city noises. I wanted to transform the learnings I had learned to process seismic data into ocean data. So just like seismic stations are used to measure ground vibrations, hydrophones are used to measure underwater acoustic noise. They're just like normal microphones, except they can measure sound under the water. And luckily, Canada operates networks of hydrophones, most of which are concentrated on the Pacific side of Canada, because that is where the most shipping traffic is. And hydrophones are mostly used to monitor shipping traffic, noises caused by wildlife as well in the water. So I applied the same analysis I had done on seismic data to oceanic data as well, and I got some pretty cool preliminary results already. I found that in the high frequency underwater noise, so usually underwater noise below 50 hertz is caused by wildlife like dolphins and other underwater creatures, but underwater noise above 50 hertz is caused by human reasons like shipping traffic and motorboats. And in the 80 hertz frequency band, I was able to measure a pretty significant dip in acoustic noise, as you can see inside the graph. And frequency bands of 60 and 70 hertz also saw a decrease in underwater acoustic noise after March. And March is when the World Health Organization declared COVID-19 a pandemic. So it's pretty significant from the data that you can observe a dip in acoustic noise during the pandemic, in which a lot of the shipping channels were slowed down. Another cool result I was to find, I also decided to plot the levels of acoustic noise in all frequency bands from 0 to 80 hertz. In orange is the levels of noise after COVID-19 lockdown, and blue is the levels of acoustic noise before the COVID-19 lockdown. So in all the frequencies above 50 hertz, the before COVID-19 levels is higher. But interestingly, below 50 hertz, the acoustic noise below 50 hertz seem to have increased. And I've been looking into why this is happening. One of the possible reasons I've come up with is that lower frequency bands became more sensitive during the COVID-19 pandemic as high frequency noise went down. So I am continuing to work on this project. Some of the future next steps I'm taking in this is expanding the project, because right now I've done this preliminary analysis for the Georgia Strait, which is located near Vancouver in the Pacific side of Canada. And there are other hydrophone networks in the Atlantic of Canada, and hopefully some near Newfoundland as well. So by monitoring this underwater noise during the COVID-19 pandemic, I hope to be able to get more insight into the effect of these lockdowns in the world. Thank you, and yeah.
Thank you very much, Artash. This was great. We also all enjoyed your website. Do you want to remind the name? Is it
monitormylockdown.com.
I think few people will have some questions for you. Okay, thank you very much.
Thank you.
Enjoy school today. That's why you had to put your first in line. Thank you. And ask please turn off the camera. And thank you. And it is now I pass the ball to Nathan here. And the floor is all yours.
Awesome. Thanks.
Thank you.
All right, I'm going to go ahead and share my screen. All right, oops, wrong one. All right. Okay, so sorry, I get texts. All right. So our team was decided to look at the carbon capture and storage Northern Lights data set provided by Equinor. You can see the contributors throughout the week. A lot of people kind of were in and out because of busy schedules and school and things like that. But anyway, it was a good group, and we were able to do quite a bit. So one of the things that we found with the data set when we first started working with it was that it's kind of obnoxious to get to the data. You have to kind of register and then go into Azure with this user interface and try to download all this data. So anyway, one of the first things that we set up was a way of kind of just downloading the data quickly for whatever purposes you have doing open data set type stuff. So you can see here, this is a listing of all the data that's in the repository for this project. It's up to 16,459 files. This started out as 800 something, and a bunch of data was uploaded during the week. It seemed to be related to the raw data for the CT scans of the core. I went ahead and did a quick analysis of how much of each kind of data there is, what category it is. So you can see there's a significant amount of core data, log data, and yeah, that's where the bulk of the data is, although some of the other categories are pretty large too. If you look at the file types, there's 15,000 of these DCM files. I think they're related to CTs, but I'm not an expert in that. There's a lot of text files, PDFs. There's SEGI files associated with borehole seismic, some core descriptions, and then a bunch of photos, obviously, for the core photos. This is the MIME type, if you're familiar with that, and counts of those. Okay. And this is, you can actually run this on MyBinder. So the data is very accessible. Anybody can run it by going to mybinder.org and then putting the repository URL in there. Just as an example, we've got it set up so you can pull most of the raw data just by the name of the key in the repository, which we've created there's a table up there that you can reference for that. So here's an example of some text extracted from a PDF. I just picked a random page from a random PDF. And then you can also set when you use this get project data thing, you can also tell it to download it to your machine if you want, or you can work with it in memory and not download it. So you have both options depending on what you want to do with it. I also started to set up kind of a higher level API. So here's the core photo one. So you can, this is all the core photos in a table format. And so you can pick like what depths you want to look at. And then you can try pulling a kind of regularized sample at any depth that there's a photo available. So like here's at 22,593.2 meters. And it tries to give you about an 8 centimeter by 8 centimeter sample. So really useful if you want to do some machine learning. If you want to look at a block of photos all kind of mashed together and cleaned up a little bit, there's a function for that. There is high-res photos. I didn't set those up to be accessible. It would be easy to do, but they're huge, and it would be really slow and difficult depending on what environment machine you're using. And also, for whatever reason, when you go into the Azure UI, you can't access that data. You just don't see it there, and I'm not sure why. But it shows up in Python, which is nice. So you could download it through Python if you wanted. Ava, one of the team members, went through and looked at the seismic data, the borehole seismic data, and here's some pretty pictures of that she put together. Let's see. Sorry, getting a text. I should have put the do not disturb on. Here's some more of the computed time, and then there's also a bunch of gather data for the borehole seismic. So thanks to Ava for putting all that together. And then Matt also gave us a line on a package to read the SPWA LA stuff. And you can pick a depth and look at what the description is for it. And in this case, I also grabbed the sample associated with it. That's what we did. Didn't have time to get to much else beyond that, but the data is very accessible through here, and there's a lot of easy ways to go in and start playing with the data and looking at it. And that's our project.
Excellent. Thank you very much.
Thank you.
It's pretty cool stuff. I'm still looking forward to see your tutorial next on my list. But now we move on. The dynamic duo, Dieter and Miguel. The floor is yours.
You can see my screen?
Yes, we can.
Brilliant. So I try to be very brief so Miguel has time to actually present what we did, because as usual, I just do some chit-chatting and Miguel is going to show some actual work. I would like to take you down history lane where the subsurface baby came from. And this is in my temp share GitHub repo. I edited that last time, 15th May 2019. So it was at Transform or late, just a bit afterwards. This was what we worked on. I took GemPy. I used discretize to get out a model with it. You don't have to understand here what we did. I plotted in a slicer that I think a few months before pushed into discretize. Then from discretize, you took it to PyVista. And then I used my forward modeler to model some electromagnetic data. And that was kind of part of Miguel's and my work on the first transform to try to bring these different tools together. At the same time, if you go here to the changelog of subsurface, there was this idea born at the chateau that we should bring all these different packages in the subsurface stack together, and there was definitely Matt, because Matt is in everything. There was Jesper was working on it, Alex, there were probably more, I don't know if Brian, Evan. There was just this general feeling we should make something, a glue to bring different packages together. And then I just want to go here quickly to the GitHub. So there was Matt in 2019, then there happened nothing. And then there was Transform 2020, and then there was Bain, and Miguel did some great work. There happened nothing, and then really Miguel started to work on, and it kind of picked up. And this, Miguel is going to show you very soon, this hackathon this year. We have now a lot of input from other communities and Python packages in the Geo subsurface stack. We already had last year, so not to forget that. Before I hand over to Miguel, I want to know two things that he will not talk about. There was the PyGimli. At Monday, they used my forward modeling code EMPyMod for 1D inversions using PyGimli, and Sogi from Simpeg worked this week on similar things for EMG3D, my 3D code to do 3D inversion in Simpeg. So just all these collaborations between different tools is what I think is the motivator for our thing. So Miguel, take it on from here.
Yes. Do you hear me?
Yep.
Good. So yeah, that was a bit the story. So one thing that we realized quite long ago is that just making one-to-one connections to the libraries, it was not going to be the best way. So yeah, Dieter, I think you have to stop sharing the screen. There you go. So that's why we started to work with subsurface. And after this hackathon in this transform, it's the first time that we have a full workflow running. So I wanted to directly show you in the documentation that's something that we have been working quite a lot, especially Dieter, this hackathon. So here we can see, for example, a tutorial how to read raw data from CSVs into pandas data frames, from pandas data frames into a Welly project, and then from the Welly project using what Rob was showing yesterday in the speed talk, the Wellpathy, or I think that now has a different name. We can directly construct the first subsurface object. And the advantage of doing it like this is that now we have a kind of a standard that we can read, for example, in GemPy. So we go from subsurface to GemPy. This is loading a bit slow. We have to do a bit of. Oh, actually, this is not. This is the one I wanted to show. So this is the subsurface object that we created before, just from the raw data. Then we can just pass it through GemPy. So GemPy understands subsurface data structures and can interpolate properties into some type of grid and expel another subsurface objects. And the good thing of this is that now GemPy, the only thing that needs to know is how to import and export from subsurface. Here in the documentation, we just started to add some external examples. So Tony from hack-segysak also was doing a from and to subsurface to his library. Karsten and Andrea has been putting a lot of work in to do the same with Pangimli. So we can come here and see. So the same model that we interpolated with GemPy, so you can just pick it where I left it, just with Pooch from Leo. So all the packages of the community are coming all together. And here, so this is a Pangimli function from subsurface, and now it's already in a Pangimli data structure that they can do some type of geophysics forward. So all these examples are in the documentation. You can just go and look at them with more time. Beyond that, as you can see, we also have the connection with PyVista for plotting. So with Welly and striplog for reading data. And GeoH5Py from Dom has been also working on that. Discretize Joe has been putting some work. Santiago also wants to join us. And that's all. So this is just the seed. This project is going to keep going. See you all next year, probably, for another hack in subsurface.
Thank you. Thank you. It's really exciting to see all these projects coming together. I think it's really something. It's really something that should make us all proud. And now we move on to Alexander. And we'll stick to another project. It's been growing within the community. So yours.
Yes, I tried to keep it short to keep the break.
That's okay. I mean, a few minutes late, it's
yeah,
okay.
So can you see my screen?
Yeah.
I guess so. All right. So yeah, as you just mentioned, the GemGis package was basically born last year during my first transform with Arthur from Brazil, and it has grown ever since. So for this transform, or for this hackathon, we basically wanted to do some maintenance work. So for those of you who don't know what GemGis is, it's basically a spatial data processing library to process all your geological data, so that we can easily put it into Miguel's GemPy and then go from there. I'm just gonna jump to the goals, what we had in mind. So we actually managed to now build the docs automatically, also thanks to Dieter, who helped out there a little bit. Here we renamed, or actually this automated building of the docs also worked with Miguel's conversion Python file to convert Jupyter notebooks to Python files for the Sphinx gallery. So I mostly have been working on fixing my notebooks, basically all the examples that you see down here and in the package to make them readable for Sphinx. We renamed the branch to Maina, which was a very small thing to do. Linked subsurface, it's not there yet. I guess we have to talk with Miguel a little bit about how we can do it, as we actually directly put in the data frames that he needs to read. We actually fixed this stupid notebook cell ID bug or error that I got. So you literally just had to change the name of the cell ID. I started to put in some interactive plotting capabilities using IPyLeaflet. So maybe some of you know the GMap package. It's from a American professor, and he has done a lot of stuff with GMap. So we tried to, not copy it, but also implement some functionality using IPyLeaflet on that. And yeah, that has basically been it. So mostly some working on the examples and tutorials, and I think it was a successful hackathon from our side. We got some useful help from the community, and yeah, I think we can go from there. I think that's it from my side.
Thank you, Alexander. It's cool stuff as always. We'll have a couple of minutes, 5 minutes break, and then we'll be back. We'll start in 3 minutes. I just need to get some water. Meanwhile, we can guys have a quick chat if you want, ask questions to each other. I'll turn off my camera and microphone for a second. Be back in 3 minutes.
Hello.
So did you plan something for the after party, Martin? No, you're muted.
Oh, I haven't planned anything specific. Yeah, no.
You didn't send beers to the house of everybody.
No, everybody to the chateau. You can see how it goes.
Come to the chateau and have a chat. That's where I'm going. I may actually go get a beer. There's a brewery down the block. So it'll be...
What time is there?
Exactly.
We're coming up on 5 o'clock UTC, right?
Exactly. It's 5 o'clock somewhere.
It's always exciting seeing what people have done after a week, especially when you head down in your own things. So, yeah, some cool stuff so far, and hopefully some cool stuff coming up.
Should have chosen a better my bedroom. My guest guest room is a mess. See that it's sunny everywhere there. There's a lot of sun from the windows. All the people. Cool. Okay, so minute-ish, and then we keep going. See some travel guide behind you, Martin.
How big yours?
I see behind you. I see some. Is that travel guides? No.
No.
Just books. Oh, just books.
And a rock. Got to have a rock.
And a duck, rubber duck. Cool. Okay, floor is yours.
All right. So I'm not sure that there's really very much to share in the sense. So what we were doing is a bit of a sprint on striplog. And what we've done with it, or what the goal here was, just to give striplog a bit of love. You can see there's a fair few issues that are still open. So one of the main ones that we identified was to try and do some work on various input and output from striplog or into striplog. So I've spent a bit of time looking at getting a more reliable, or at least a bit more flexible CSV reader. Brian Burnham started having a look at a 2 dictionary, and then from 2 dictionary we should be able to extend that to make to JSON as output formats. We've also got some small bug fixes that we did that have come up. So Rob did a couple of those. One of the things that it's not completely hooked in yet, but going forwards, intervals will have a name attribute. So that's sort of available, but we need to just edit all the constructors so that that actually gets used. But yeah, we think we've made a bit of forward progress there. You can see sort of in the last few weeks, or in the last week or so, we've had a couple pull requests that are open, but we've closed a few more. So yeah, hopefully that means that this will be a more useful package for people, and that we're going to try, or going forward, the idea is to try and iron out some of the inconsistencies internally and with the API to make it a little bit easier to work with. So yeah, Zane, let us know if this breaks litholog. We'll try not to, but we'll see what happens. You're muted, Fabio. Filippo, you're muted.
Yeah, I'm muted. Not anymore. You have a couple of minutes if you want to say anything else. Otherwise, we'll just... Oh, he disappeared. I lost him. Okay, then I guess we'll just move on to the next dynamic duo. We met, and or it's yours.
All right. So I guess you don't really need to. So I'll be talking, and Matthew's going to be driving because I can't talk and drive at the same time. But this is wellcorr, the swell way of correlating wells. This is the collection of people that are involved with this project. Note how we're distributed geographically. This is kind of obviously something you can't do in an in-person event. There's a bunch of other information on this slide that will let you know what we've been up to. So we've got an app actually running up here. We'll get to that in a second, but if you want to try that out, it's running and operational. So this collection of people, let's face it, we don't really know what we're doing, but we are united by this dream of having some kind of web app that allows us to work with logs, pick tops, and other geological features and make cross sections, and obviously then access that data so we can use it in other applications. We picked up on this project from last year that was done. I think it was called Well Dash or something like that. And that may or may not have been a wise choice, but we wanted it to start simple, and we've tried to keep it simple. The challenge will be to keep it that way as we build more features into this. So this is using Welly and striplog under the hood. So, both are pip installable, and we've used the Poseidon data set that Peter Borman's made available. And we've, there's links to that in the data underground. And the idea here is there's different points of entry into the app. A user can upload one or more LAS files and build up a sequence of logs into a cross-section, and they can upload any number of formation top sets that they can then edit and manipulate. So Matthew's showing an example here for the Kronos well, or he's going to the Poseidon well, and which is empty right now, and he can actually go in and pick different formations. And striplog has this knowledge of when you're picking a top, that it's also going to go down to the formation beneath it. So we think that's pretty cool, and you have almost a nearly responsive kind of behavior. We've paid sort of attention to not have the x-axis wobble around as you're zooming, so geoscientists will enjoy that. And so as he's picking out the strip log, if you like, and defining the tops for this Poseidon 2 well, you can see he can select from the existing wells in the database, and maybe if he defines one more beneath the Jameson formation, he can show us that you can actually create a new pick. Let's call it the software underground formation. Maybe there's a pun in there. And you can see that you can pick that just like any other curve. And now that it's added, he can edit it, and you can see that updating on the cross section. And now you have that in the data table. And so that data table is also a nice feature. We can, he's already filtered on that data table. You could copy that to a clipboard, throw that into a data frame, or dare I say, an 800-page drilling and completion report, which is where you typically find this information in the first place. So we're pretty proud with what we've achieved. Obviously, the data set's kind of fixed and tailored, but we think we have ways of making that more flexible for people to use. Things like flattening the cross-section or picking intervals, like perforation intervals or lithologs. I think all of these things are options. So let us know what you think of this app and where you think it should go.
Yeah, I find it really exciting because we're at a point now that, it works as a web app. It brings into, can we do crowdsourcing of geologic tops and all that kind of fun stuff. But as a project, it was a lot to learn and a lot of fun to do. So I'm glad that we're getting to release it to the community.
Sort of, as a demo.
Yeah, I lost track of our time. How much time do we have left?
I started a clock. I think we're just about out of time.
All right. I will stop share.
Cool. Who designed the logo?
Yeah.
The logo was Brian Burnham's artistry. So thank you for that. Yeah, we tried to use the swung colors. So
didn't want to diminish everything else, but it was amazing. Cool.
Branding is important.
Yeah. Everything. Excellent. We can keep going. Next line is Justin. And the floor is yours.
All right, let me see if I can share my screen less horribly than the last time. All right. And can you see slides?
Yes.
Okay, great. So on my KV, we did talk like this morning, so there are slides above here, but we're going to start on slide 15, which says more visible connections between projects can nudge developers in a way that strengthen open source community. In this one, we're going to talk about connections between code and dependencies and multiple code projects that share the same dependency. So my kind of hypothesis is that making visible the connections between projects and dependencies can provide huge motivation to contribute to your project. And I'll give a great example of this. Typically, no one actually knows what all their open source code contributions are actually used for. I don't think we really think about this, but you literally like make things and then people use them for things and never tell you what they use them for. If you like actually find out what people do with your contributions, that can change things sometimes. For example, GitHub earlier this week put a Mars helicopter badge on the 12,000 developer profiles that had contributed to a code project dependency that was used on the Mars helicopter. And on Twitter, developers were like flipping out about this, is probably the best way to like describe it. Joe, who's a member of Swung, got the badge here, right? And so many people were really excited to know their like code contribution to like a project somewhere was somehow used by another project, which was used by another project, which was used to fly on Mars. So the hypothesis is the kind of second part of it, better visibility into the networks of this project can actually drive additional contributions and also direct where they happen, which otherwise wouldn't happen. So this doesn't just apply to powered flight on Mars, but also to subsurface geoscience software as well. Question mark on that one. And then one question people might have is, why isn't this already widespread? That's, I think, largely because the actual data and the technology to do it well didn't exist until not very long ago. I tried to do a similar project back in 2017, 2018, and the data quality I could get in terms of dependencies was generally pretty horrible. And so you couldn't do that much compared to what you can do now. So I've taken a repository from Lawrence Livermore, and instead of having it get all this data from the GitHub API for their code, I directed it at open source geoscience code. So you can see here all the repositories that I'm tracking, and how they've increased over time. It's actually a very nice curve there, I think. And then these are all represented by two dones them, and you can click and see the projects here, and then click in and see the contributors here, which is kind of nice. And if I click out and go down, there's some more stuff here. I'll just show a couple of things. So this lets you see the stars over time, and it's interesting to like see different patterns there. Some of them start kind of slow and then get faster, and other ones start very fast and then kind of like plateau over time. And there's data on tissues and pull requests, and so like this is interesting for seeing which projects are very stale and which ones are not. And then there's some other stuff here which I'm going to skip over for time. These are the repositories scaled by popularity here. And some more stuff I'm going to skip. This is a network graph of all the code connected by their dependencies, which is pretty cool. And so the driver script is in yellow and Python's in blue, and you can do cool things like you come down here and see all the because I have a window and a window, this doesn't like the search. Okay, pandas. Okay, click pandas. So these are all the code repositories that I'm tracking that use pandas. So if you want to do geoscience stuff and you want to practice pandas, these are a starting point here, and you can see which libraries are used as dependencies, etc. And so a good way to think about this, I think, is connections, if they're made visible, can nudge blank. So I've got a few of them here, but I'm thinking I'm out of time.
Thank you, Justin. This is beautiful. It's always nice to see all this project merging together, and there's very nice visualization. I like the growth of the citation. What was that? But anyway, thank you very much. You should share the link. I think I've probably already done that on the various channels. Cool. Then show must go on, and so then okay, there you are. I must say that I'm not sure how to pronounce your names. Elvin? Okay, I think you're on mute. We cannot hear you. Nope. Cannot hear you. Still not. Nope.
Anything better now?
Yes. Yes, we can.
Wow. Just that simple. Okay. Yes,
Okay.
Elwin is how you pronounce my name. So yeah, I'm going to share this project. I'm going to share my screen, hopefully. Be this one. Yes. Okay. Great. So, right, presenting our hackathon project. So we've been working this past week on something we've started as T21 Hack Footprint. So we've got our channel on the Slack, and we've had quite a bit of collaboration going on with that. So when I say we, who are we? Okay, so our team includes Matteo Nicoli, Wesley Banfield, Leo Dinendra, Marco Gok, and myself, Elwin Galloway. And you've got some other handles you might recognize as well. And right, so this team came together. Matteo and myself, we had come across some challenges when it came to seismic acquisition footprint through just through some of our work, other work, and had some ideas about how we might tackle that, but we lacked some of the skills necessary to do so. So we, at the pre-hack presentations, Matteo described some of the aspirations of the project and some of the skills that we needed, which were some of the visualization or interactivity for the app that we had in mind, or the tool we had in mind, as well as some of the sort of efficiencies in computing that we would need to manipulate some of the larger data volumes that we wanted to use. And so we put that call out, and Wesley, Leo, and Marco answered that. And so we've been working this past week on our tool. So I'm going to show some images just to explain what we're trying to do. So seismic acquisition footprint. In seismic data, you can recognize it in this time slice as this sort of cross-hatched pattern that we see. And the other thing, or you can see in section, as these sort of vertical bands that come through the section. Now, it's also recognizable in this time slice as these slight lineations. So it's sort of a noise that comes through in the data in both time slice and section. And it's challenging for a number of reasons. It affects the interpretability of the seismic section through some of the automated horizon picking. It also affects some of the attributes you might calculate from the data. So there's some solutions to this, and some of those are more expensive than others. So instead of sending this back for reprocessing at the seismic processor, which could take time and money, we wanted something to be able to do to process the data on our local machines, or be able to do it quickly and easily by ourselves. So seismic acquisition footprint, you might have recognized, is sort of a repetitive linear feature, and because of that presents an opportunity. Now, if we transform these time slices into the KX, KY domains, we're looking at spatial wave numbers, they start to cluster in that in the spectral representation. So, for instance, these synthetic vertical lines, these are representing some variations in amplitude on a time slice. They would gather here, cluster in the spectra, and these ones would look like this. So if we can identify those in the 2D spectra for a time slice, we should be able to suppress them or remove them. So the idea here's as an example, an image affected by this. It's not random noise, coherent noise. When we convolve it into the 2D, or when we transform it into the 2D using 2D FFT, we can see these 4 points that are related to that noise. And so if we can identify it and suppress it, we can reject it and keep our cleaned up image. So that's the idea that we wanted to accomplish. So we've had some success, and we want to introduce Frida, the footprint removal interactive design app. And so we're going to cross our fingers and try a live demo here. Okay, so in the app, what we have is some interactivity. So we've imported our data, and we have some slices here. We've got 2 different time slices, a shallow and a deep.
Alvin,
so we get
can I ask you to stop sharing and resharing? There's some lag on the screen. This might help.
Okay.
Just quickly stop sharing and resharing your screen just to see if this helps.
Okay. This one. Okay.
Now we see
that helps. Okay. So we have some interactivity. We have shallow slice and a deep slice, and we have up top an FFT spectrum of the shallow slice. So we can select a certain slice, and what we're going to do is design our, I'm going to zoom in here to make it a little bit larger for everyone. So we can just design a filter based on the spectrum. So the noise that I'm trying to remove, and I'll bring that in here, are these vertical lines. So that's not geological, that's just seismic acquisition footprint. So we want to remove that. And the lines, because these lines are vertical, they sit on this sort of horizontal line on the FFT spectrum. So I want to suppress that part of the signal. So I'm going to highlight it here, and you can see it's here in the filter window. This is the filter that we're going to apply to the spectrum. I'm going to select another bit over here. Okay, so I've designed a filter that suppresses the footprint, and so starting with our input data, this is the filtered result. Oh, filtered result, and this is the difference. So, and you can see how that appears as a deep as well. So we've been able to just interactively design a filter to remove that footprint. And if I do this and save, I'm going to reload this app with some different data and then show again another example quickly. So here's another example. This is a different data set, and there's a couple different aspects of noise here, footprint.
Alvin, I think we are a bit out of time, and I think the same problem is, could you able to share this app later? And I see that now is running your computer, right? So we would, we could definitely also help with AWS to host it. Some connection, I don't know. It's connection on optimal, so it's a bit difficult to.
Right. The one thing I should mention is it is deployed with one of the data sets on the Amazon Web Service, hosted by Swung. So that the address for that is down here at the bottom of this slide, which we'll find a way to share.
Okay.
But that's the project.
Share either in the main channel or in your project channel. Cool. Thank you very much. Then we move on to Tony, which will tell us everything about the Swiss Army knife.
Yeah.
What is yours?
All right, sharing my screen. Wrong one. Okay. Okay, hi everyone. The hackathon I was running all week was another sprint for a package called Hack-segysak. If you're not familiar with it, this is a package returning from Transform 2020, where it was kind of born, and it's now matured to the point where we're offering Hack-segysak as a relatively stable kind of package through PyPy. It's designed to essentially ease over a lot of the pain of loading Segway data into Python and returns the data to you in a labeled X-ray, essentially making life much simpler. It's primarily been me working this week, but we've had some new contributions, valuable contributions to the documentation from Chris Deneen and Richard Scott, and also some late contributions from Sam Potter. So thank you to everyone who's had a look at the project and provided feedback this week, and also all those that have contributed in the past. The primary goal this week was to basically get through the version 0.3 project, which had been kind of languishing since last year, and I'm pleased to say that we've been able to do that. We've sort of ticked off quite a few issues and delivered quite a lot of new content, bug fixes and testing and just today released version 0.3 of the package. Some of the key highlights from that release are baked in ZGY support. So if you're a Patrol user or you interact with the OSDU universe, we've now kind of released OpenZGY as part of Segysak, so you can use that to read ZGY data. We've offered performance improvements, significant performance improvements for arbitrary line and well path selection. There are some new functions for loading seismic data that allow you to handle multi-dimensional or arbitrarily dimensioned seismic data, not just 2D, 3D, and gathers. We were able to add some support now for the subsurface package, which you heard about earlier. So that's now been included. And I think most importantly, there have been a significant number of new examples added, including the tutorial, the 2-hour tutorial that was run earlier in the week, which includes a YouTube video and a full notebook. The big new examples include extracting along well paths, which uses the well path py library, another one of the great subsurface developments, and working with 3D gathers. So we now sort of offer an example showing you how to deal with 3D gathers. And finally, a couple here on merging seismic data cubes with different geometries and reading and writing to ZGY. Another big part of the documentation that's been updated this week is the contributing guide. This is based on the work of, on the contribution guide in the Fatiando project. So a big thanks to them for helping out with that. We've got a few slightly different bits of content in here, but essentially, if you feel like Segysak is something you want to contribute, this is the first point of contact. I think over to you.
Thank you, Danny. Great work. So we are done with the official list. However, I got Alan Richardson sent me a video, like a 1-minute video of his web viewer for Segway. I'll try to do some play it on my computer and do some screen sharing. Hopefully that works. So let me share my screen. Do you see this, my VLC player? Okay.
Yeah.
Can also play, it's a very short video.
Hello. Hackathon, I wanted to create a web browser-based Segway viewer. There are already lots of free Segway viewers, but you need to install them, and often they only run on Windows, whereas with this, there's nothing to install, and it runs on any platform. I'll demonstrate it by opening the mobile AVU Viking Graben line 12, which is an open dataset. You can see that we're looking at one shot gather. We can look at a different shot gather. Change the amplitude clipping so that we can see the fainter areas more clearly. Look at the file headers, the textual file header and the binary file header. And adjust the settings, for example, the color map. We can also zoom in on parts of the data and pan around. So I got it working. I did encounter two problems. One of them is that performance is a bit slow. And the second is that I found initiating file reads from a web app is also slow. This means that I can't scan the trace headers, which I would have liked to be able to do so that users could view all traces that have particular trace header values. But hopefully it's already useful to some people and that the problems will improve over time. you can access it at segway.io.pages.dev.
Okay. Yeah, that was a nice web app. Hopefully, I mean, you can ping Alan. I don't think he had a project channel, but you know, he can ping you directly on Slack and ask questions. Okay, well, we are done with the presentation. It was a blast, as always. I have a lot to catch up watching all the tutorials on YouTube. Thanks everyone for presenting this funny time for this few minutes presentation. They were great. I saw some activity on the Hackathon channel on Slack. I just want to conclude saying that we're really looking forward to next year. There is always plenty of activity happening throughout the year. We'll keep posted on Slack, the rendezvous organized by Steve and so on. I just want to conclude with a last announcement that Chateau is open, will always be open. So I'm going to close this. I'm going to close this live stream. Thanks again, everyone. And I'll see you on the Chateau for a virtual beer, virtual Coca-Cola or whatever. Thank you, everyone. It's been